Hello, I'm Dr. Du-Han Lee. I'm going to talk about how to use the top consolers when prescribing progressive lenses in clinical practice. At the beginning of this lecture, how to apply single progressive lenses and progressive spectacles using top consolers will be discussed. Later on, I'll give you some tips on prescribing progressive lenses using top consolers. You can use the top consolers to make sure the progressive lenses you ordered were made correctly. I'd love to show you actual photos of the lenses, but to avoid revealing any specific brands, I'll use a drawing instead. The most important thing is to check the refractive power of the lens. After measuring the lens with solos, we compare the spherical, cylinder, axis, and add values to the prescription. In this case, there was some unwanted astigmatism of a minus 0.14 diopter in the distance power, and the add was slightly higher than the prescribed value. Now, let's check the markings on the actual lens. Solos marks the points with the highest refractive power in both the distance and near vision areas. The distance reference point should be within the distance verification circle, and the near reference point should be inside the near verification circle as well. Just be careful not to confuse the three markings in the distance vision area. These don't show the horizontality of the lens, but rather the cylinder axis of the lens. You also need to check the inset by measuring the distance between the distance reference point and the near reference point with a ruler. Now, let's check the corridor length. Corridor length generally refers to the distance from the fitting point to the top of the near verification circle. When checking the corridor length using the progressive graph, remember that 0 on the vertical axis represents the distance reference point, not the fitting point. So, to figure out the corridor length, start from the point that shows the distance from the distance reference point to the fitting point, which is just below 0 on the vertical axis of the progressive graph. From there, look for the point that is lowered by this prescribed corridor length from the vertical axis. Then, find where this point intersects the progressive graph curve and check the edge amount on the horizontal axis at the spot. Now, let me explain how to interpret the change rate of refractive power using the progressive graph. First, draw a straight line connecting the start and end point of the curve on the progressive graph. If the curve is below this straight line, the change rate is slow. And if the curve is above it, the change rate is fast. Next, find the points where the slope of the curve starts to get steeper and where it becomes flatter. For this graph, the slope starts to steepen 5 mm below the distance reference point and flattens out starting at 13.5 mm below. This means that the change in refractive power is fast between 2.4 meter and 70 centimeters in front of the eyes, and it's relatively slow at the other distances. Let's take a look at the new case. The power for distance correction is slightly higher than the prescription, but the power for near correction is much higher than what's prescribed. The distance reference point is within the distance verification circle, but it's almost at the upper edge. The near reference point is located below the near verification circle. In cases where the distance reference point and the near reference points are significantly farther apart than usual, it's expected that a lot of eye movements will be needed when switching between distance and near distances. Even though the NRP is outside the near verification circle, the S at the NRP is greater than the prescribed value. So, we can expect the required add to fall within the near verification circle. As you can see, the horizontal distance between the DLP and NRP is similar to the prescribed inset. You can expect a smooth change in refractive power because of very long vertical distance between the DRP and NRP. This is supported by the narrow gap between the curve of the progressive graph and the slope connecting the DRP and NRP. The area where the refractive power change is slow is wider than the area where it's fast. So, adapting to the transition from distance to intermediate viewing distances will be easier. If you check the edge amount at the point corresponding to the corridor length in the progressive graph, you will see that about 85% of the prescribed edge is secured. Since the refractive power at the DRP is higher than the prescription, even with an edge of plus 0.25 diopter at the fitting point, distance vision will still be good enough. Looking at the slope of the curve in the progressive graph, the change in refractive power is slow up to viewing distance of 1 meter, and it becomes slightly faster at shorter distances. Looking at the distortion map, it seems like the corridor length is longer than what was prescribed. This is because the measured locations of the DRP and NRP are quite far apart. So, you might think that the lenses were not made according to the prescription, but that's not the case. In fact, the prescribed corridor is actually located within the corridor shown in the distortion map. As a result, the distortion-free area at the actual fitting point and near vision area will be relatively narrower. Since there's no astigmatism prescription, you can see that the distribution of spherical power is symmetrical based on the corridor in the spherical map. Also, the change rate of spherical power is almost uniform, which is because the distance between the DRP and NRP is quite long. In this map, the expected locations of the fitting cross and the near verification circle seem to have a slightly insufficient spherical power for distance vision, but are sufficient for near vision. However, this trend could change if there's unwanted astigmatism, so it's important to check the SEQ map again. The SEQ map shows the distribution of equivalent spherical power, which takes into account both the prescribed and unwanted astigmatism, as well as the spherical power. Unlike what we saw in the spherical map, the spherical equivalent power at both the fitting cross and near verification circle is expected to be lower than prescribed. Additionally, the change rate of spherical equivalent power is relatively slower until the middle of the corridor. As a result, if the height of the spectacle frame is not enough to include both the DRP and NRP, the wearer may find both distance and near vision unsatisfactory. In the prism map, only the weak prisms near the fitting cross are affected, so you will be able to use binocular vision more comfortably at distance and intermediate gazes. When a new patient visits, it's important to mark the distance and near reference point rather than just measuring the lens with the solos. While you can determine the positions of the DRP and NRP with a conventional lens meter, it's difficult to pinpoint the exact locations. Now, take a look at this picture. As you can see, both DRP and NRP are easy to find. The first step is to compare the positions of DRP and NRP. If the optical heights are the same for both lenses, the vertical position of the NRP should match on both sides, ensuring comfortable and clear near vision. Additionally, the NRP should be positioned closer to the nose than the DRP, and the horizontal distance between the DRP and NRP should correspond to the inset. In this picture, the vertical positions of the DRPs on both sides are similar, but the NRPs are different. Also, the inset is correctly set on the left lens, but on the right lens, the DRP and NRP are nearly at the same horizontal position, leaving almost no inset at all. As a result, A patient wearing these glasses might complain about poor near vision. Shall we move on to the SOLOS measurement result? Refractive evaluation can be used to discuss the optical characteristics of the progressive lenses the patient is currently wearing. First, you can see that the spherical power distribution is almost symmetrical on both the temporal and nasal sides based on corridor. This symmetry ensures that both eyes experience similar optical effects in peripheral vision, which leads to better visual balance, clear vision, easier adaptation, and greater comfort. When comparing the spacing of the color bands, we can see that the spacing is looser for both distance and near vision, while it's tighter in the intermediate zone. While distance and near vision may feel comfortable, intermediate vision might become tiring more easily and could lead to disorientation with eye movements. Now, let's take a look at the distortion map. As you can see in the previous image of the spectacles, the position of the DRP on both lenses is almost the same in the distortion map. However, the NRP on the right lens is positioned lower than the left lens, so it's slightly cut off. Additionally, the NRP on the right lens is shifted to the right compared to the DRP, while on the left lens is the opposite. Because of this, the peripheral distortion area on the lenses shifts more to the left than the temporal sides, and the distortion here is quite noticeable. While the clear viewing zone from distance to near is relatively larger, the spectacle wearers may find it difficult to adapt due to these optical characteristics. So, it's important to figure out whether the patient's symptoms are related to this. Now, let's take a look at the prism map. As you can see, weak prism power is spread out widely across the distance and near zones. This helps maintain more comfortable binocular single vision at both distance and near, with less disruption to eye alignment. Additionally, a gradual and consistent change in prism power helps avoid visual instability when moving the eyes around the lenses, both at distance and near. However, the relatively higher prism power in the intermediate zone is more likely to cause subtle image shifts or visual discomfort. Because of this, spectacle wearers may feel dissatisfied with their intermediate vision. Therefore, optometrists or opticians need to help them select progressive lenses designed to improve intermediate vision. The SEQ map makes it easy to analyze the optical characteristics of a lens by showing the overall refractive power, including cylinder power, as a single value. Just like the spherical map, you will want to check the symmetry of the SEQ power distribution in the lenses using the SEQ map. As you can see from the current measurement result, both lenses show similar symmetry in the SEQ power, which suggests good visual balance, clear vision, easy adaptation, and greater comfort. However, adaptation might be a bit tricky since the color band spacing in the intermediate zone is narrower than in the distance and near zones. The asymmetry in the NRP position is also likely to affect near vision. To summarize, people who spend a lot of time on the computer while at a desk may want to consider a lens design with stable SEQ values in the intermediate zone, as well as adjustments to the NRP position. Once the eyeglasses prescription is complete, optometrists and opticians should go over the characteristics of the current lenses with the patients and explain the lens design needed to minimize symptoms. In the next session, we'll look into how to use the SOLOS solutions based on patient symptoms and needs in real clinical practice. If you look at the distortion maps on the left and right, you probably notice that they are quite similar. The sharpness of the field of view at intermediate and near distance is about the same on both sides. and distortion is mainly focused on the lower corners on both sides as well. However, the left map shows that it maximizes the sharpness of field of view at the center, while the right map has a sharp field of view that's wider than other focal distances, but still narrower compared to the left. Additionally, when you look at the changes in distortion, you can see that the spacing between each color map is narrower on the left than the right. So, with the left lens, you can get a wider sharp field of view, but the distortion changes more quickly and intensely around the edges. As a result, just a small movement of your eyes to the left or right might make you feel like letters or lines are bending or shifting. On the other hand, the right lens has a narrow sharp field of view compared to the left, but since the distortion changes more slowly around the edges, you are less likely to experience the image swim effect, making for a more comfortable viewing experience overall. Now, let's compare the SEQ maps. When you look at the distribution of the SEQ power for clear vision in far near distances, the left lens has a significantly higher amount of clear vision in the far distance. On the other hand, the right lens has a more balanced distribution of refractive across far, intermediate, and near distances. For the left lens, the power change near the DRP is gradual, but as we move from intermediate to near distances, the power increases more quickly. This could result in discomfort when shifting from one focal point to another, especially in up-close viewing. The right lens, however, has a gradual increase in power from DRP to NRP, and the color change happens slowly as well, which helps reduce eye fatigue and offers a more natural transition between focal points. This trend is also reflected in the progressive graph. So, to sum it up, the left lens excels at providing clear and comfort vision at distance, while the right lens provides a smoother and more balanced clear vision across far, intermediate, and near distances. When the prism distribution in both eyes is symmetrical, it's easier to maintain binocular single vision. Looking at these lenses, we can see that both have a slight prism distribution around the DRP area. While the prism effect on the left lens extends over a wider area compared to the right lens, the difference is minimal, so maintaining binocular single vision shouldn't be a problem. We also observed that around the NRP area, both lenses have almost the same level of prism power. Again, this symmetry suggests that maintaining binocular single vision will be relatively easy. However, the relatively higher prism power around the NRP area could cause the image swim effect when transitioning gaze from DRP to NRP. In summary, when the prism distribution in both lenses is symmetrical, adapting to progressive lenses is likely to be easier. The area where the prism power has weak effects are different for each lens. For the right lens, it's near the DRP, while for the left lens, it's around the center of the corridor. As you move your gaze from the DRP to the NRP, different prism powers apply to both lenses, which could make it more challenging to maintain binocular single vision. The differences in the positions of the NRP and the corresponding prism power on each lens could also make it harder to use binocular vision at close range. When different levels of prism power between the lenses exist, binocular disparity can occur, which could lead to visual inconsistencies. This may cause excessive eye strain, fatigue, and even headaches. As you can see on the screen, when the distribution of weaker prism power is symmetrically spread from the DRP to the NRP across both lenses, the binocular disparity decreases. This makes it easier for the eyes to converge during gaze shifts, which makes it much easier to maintain binocular single vision. As a result, the wearing comfort improves significantly, and adapting to progressive lenses becomes faster and more effortless. Looking at the distortion map on the left, you will see that the length between the DRP and NRP is quite long at 29 mm. The spacing between distortions is wider, and the peripheral distortion is relatively small. This characteristic provides a more stable field of view even when the eyes are moving frequently, which can help reduce fatigue during extended use. This makes it ideal for patients who have a lot of eye movements. On the other hand, if you look at the distortion map on the right, you will notice that the length between DRP and NRP is shorter at 19.5 mm. The spacing between distortions is narrower, and peripheral distortion is more widespread and stronger. This characteristic is better suited for patients who have more head movements rather than frequent eye movements. When someone with a lot of head movement shifts their gaze, they tend to move their head instead of just their eyes. This means the whole lens moves together, leading to a more stable focal point adjustment. Since head movements change the position of the entire lens, it can avoid the area where distortion is concentrated, making it less likely to feel the image swim effect, even if the peripheral distortion is stronger and more widely spread. For people who move their eyes a lot, having a slower change in refraction makes it easier to focus. Looking at the left SEQ map, you can see that the intervals between SEQ powers are relatively wider. If you look at the slope of the progressive graph, you will notice it's flatter from far distance to intermediate, allowing for smoother refraction transitions. This is possible because the distance between DRP and NRP is quite long. On the other hand, for people who move their heads more, having faster changes in refraction makes it easier to focus. If you look at the right SEQ map, the intervals between SEQ powers are relatively narrower, and the slope in the progressive graph is slightly flat at the center, but from intermediate to near distances, it becomes relatively steep. So, the refraction transition is faster compared to the left lens. Therefore, even if the eye movement is minimal, when switching focal points, head movements can help adjust the focused area needed, making this design easier to adapt to. Pupil diameter is also a factor to consider when choosing progressive lenses. Small pupils are not exposed to peripheral distortion area when moving along the corridor, so clear vision can be maintained. In contrast, large pupils are easily exposed to peripheral distortion area when moving along the corridor. Peripheral distortion exposed within the pupil reduces visual clarity and satisfaction. Therefore, if the patient's pupil diameter is large, it's recommended to select a progressive lens with a wide corridor width as possible. So far, we have looked at the clinical application of progressive lenses using Topcon Solos. For more information, please check out Topcon Healthcare University. Thank you for watching.